Hey there, internet people! Today we're diving into the chaotic journey of creating fluid simulation in Unreal Engine. And when I say diving, I really mean drowning in technical documentation while my CPU begs for mercy. So why did I decide to torture myself with fluid dynamics? Well, here's the thing. I'm not a game developer, I don't even write C++, and these days I barely ever write any code anymore. Which is one of the reasons why I'm itching to just write some code and build some shit. And most likely break some shit too. But I'm a gamer, and every couple of months I open up Unreal Engine, mess around with some blueprints because I have an idea for a game, then after a week I give up because it's too hard. But not this time. This time I actually feel really motivated, I think I have a decent idea, and I really want to see this through. But that's not why we're here today though. Okay, so first let me preface this.
Look, here's
We're
the
gonna
thing.
be fine. Listen,
I'm gonna be honest with you. I'm kind of retarded.
So for my game, I wanted water that actually flows and can fill up underground caves naturally. With all the existing solutions like fluid flux, which looks amazing by the way and behaves really realistic, it uses a camera projection, which means it's only really working on the surface. Not good enough. I need real fluid dynamics, baby. Water that obeys the laws of physics, water that respects itself. But hey, how hard could it be, right? It's just solving the Navier-Stokes equations, implementing voxel-based simulations, and making sure my computer doesn't achieve liftoff from overheating. Easy peasy. Oh, did I mention that solving Navier-Stokes in 3D is literally one of the unsolved Millennium Prize problems? You know, those math problems so hard that they'll give you $1 million if you solve them. So basically, I'm trying to solve $1 million math problem for my indie game. Seems reasonable. Now, the first step in any dev journey, pretend you know what you're doing and Google everything. After watching approximately 42 YouTube tutorials at 2 times speed and realizing none of them actually solve my problem, some random person has a video of something like this, 30 seconds long, no details at all on the implementation, like bro solved the problem and just left. The closest things are Thule's implementation and John Lynn's, but there are no actual details on their implementation, how they did it or what tools they use. So I did what any sane person would do. I went deep, and I mean deep. I studied every falling sand simulation out there. I dissected Noita's entire engine. I even studied VRH3's water implementation. And the wildest part, there is nothing on the Unreal marketplace that does what I need, not a single asset. At this point, I would have probably paid anything just to save my sanity, but here we are. So the rabbit hole got deeper. Eulerian methods, Lagrangian methods, semi-Lagrangian advection, words I definitely couldn't pronounce correctly the first time.
And I've decided that I want to die.
Alright, so for about the first 2 weeks I decided to try the Cellular Automata approach. You know, the classic Conway's Game of Life, but for water. This is pretty much what Minecraft does, and it does work pretty good. The more I played with it, the more I realized it just didn't feel right. The water moved like some weird alien jello, not like, you know, water. Well, that was approach number 1. Now it's time for the big guns. So as it turns out, fluid simulation is just a bit computationally expensive, not to mention that it's complicated. For those of you who aren't familiar with fluid dynamics, don't worry, I am not either. Let's imagine trying to calculate the movement of every single water molecule in real time while also trying to make it look pretty. So the main approaches are usually grid-based methods, Eulerian, particle-based methods, Lagrangian, some hybrid approaches, or just giving up and using a normal map like a sane person. So what did I do? I went with option 5, all of the above, in that order with increasing desperation. Alternatively, the game could always be set on Mars or something. Day 45. I haven't seen the sun in what feels like years. My dreams are filled with velocity field and pressure gradients. At this point, I've spent every living moment of every day obsessed with this. I was starting to understand why no one has done this before. And that's when I found it. I was watching the Coding Train's video of fluid simulation, where he used someone's code from 3D to implement the fluid simulation in 2D. That someone was Mike Ash, and he wrote his thesis paper on exactly the problem I was trying to solve in 2005. So thanks to Coding Train for linking the blog post Fluid Simulation for Dummies. Yeah, I'm a dummy. This is perfect. So the paper outlined this brilliant approach using a grid-based Navier-Stokes solver that could actually work in my voxel setup. Let me walk you through this masterpiece of a blog post. Mike Ash's Fluid Simulation for Dummies is what happens when someone really smart tries to explain something really complex to people like me, top 86 percentile IQ enjoyer. So here's the basic idea. You've got this grid, right? And in each cell, you track velocity, which is just a fancy talk for which way is the fluid moving and how fast. First step, advection, which is just a fancy word for stuff moving around. To that end, it looks like each cell in turn in that cell and grabs the velocity, follows that velocity back in time and sees where it lands. It then takes a weighted average of the cells around the spot where it lands, then applies that value to the current cell. That makes sense.
What? Bro, what are you talking about, man?
Step 2. Diffusion, or as I like to call it, smooshing the velocities together. To go to Mike here, while I know what it does, I don't really know how. So let's move on to step 3, projection, aka make sure water doesn't magically appear, disappear. The blog says, just solve the system of linear equations like it's ordering a coffee. This is the part where Mike casually drops the whole solve Poisson equation thing like we're all PhD mathematicians just hanging out. Admittedly, Mike did not exactly understand what the linear solve function does or how it works. Luckily, I'm built different, and I have access to a comment someone left on the blog post which details exactly what it is and how it works. Unluckily, I am far too stupid to understand any of it, so I'll leave this as an exercise for the viewer.
Hey girl, I'll see you tomorrow.
But the genius of Mike's blog is he breaks it down into these simple little steps that even I could implement. It's like cooking, but instead of a cake, you get computational fluid dynamics. And the best part? He literally says, don't worry about why it works, just implement it. And you know what? He was right. I spent about 3 days translating the paper into Unreal Engine code, debugging pointer errors at 3 AM while questioning my life choices. I still don't fully understand why it works, but it does work, and that's all that matters in my book. Actual, realistic, fluid dynamics. Look at that beautiful, physically accurate voxel water. Woo!
Daddy, chill.
Alright, so after playing with it for a little bit, something becomes really obvious. It's running at like 3 frames per second, so it's time to optimize. And this part of the journey involved a lot of memory management nightmares, crying softly at 2 in the morning, and lots of parameter tweaking. The real game changer though? Octrees, baby. What's an octree, you ask? It's like a tree, but octa. 8 children per node, recursive spatial partitioning, hierarchical data structures. The basic idea is you divide your 3D space into 8 parts, then divide those parts into 8 more parts, and so on. This way, you only simulate fluid where it actually exists. How does it work exactly? Well, don't worry about it. The implementation was just a tiny bit complex, only took me about 37 attempts and 1 existential crisis. If the node is null, but its parent isn't, but its parent sibling, second child, is pointing to... Wait, what was I doing again? But then, it finally worked. My simulation went from melting my GPU to merely making it uncomfortably warm. Progress. Alright, after way too many hours, here's what we've got. Now I know what you're thinking. That doesn't look like water, there are just some colored boxes. And you're right, Right now, it's just a debug visualization. Some blue boxes showing where water exists and cyan boxes showing flow direction. It's definitely not pretty yet. And is it optimized? Well, let's just say there's room for improvement. But the physics work. That's the hard part. The water actually flows correctly, fills spaces, and behaves like a real fluid. The next steps are making it actually look like water and optimizing it so my computer doesn't melt through to the Earth's core. But here's the exciting part. There's nothing like this on the marketplace, so if I can get this working and looking good, maybe this suffering will pay off after all. The cool part about this implementation is that it's not just a water system being a fully fledged fluid simulation. It can work for things like lava, honey, smoke, fire, other fluids. So, what did we learn from this journey? Sometimes the thing you need doesn't exist and you have to build it yourself, and close enough is good enough. Oh, and if you work at Epic Games and you're watching this, please don't steal my idea, or at least hire me if you do. If you enjoy watching me struggle, make sure to like and subscribe. This is the first time making a YouTube video in this format, so let me know what you think in the comments below. I'll leave all the useful resources in the description and a pinned comment. Next time, making this thing actually look like water instead of a Tron fever dream. Catch you in the next one.